So in this semester, we have a subject called Peripherals in Embedded Systems. And it is a continuation of the previous semester's subject, Embedded Systems Architecture. So in the previous semester, we studied how the microcontroller core is built and what's inside the CPU. And with this knowledge, we will continue and we will look in this semester at peripherals of microcontroller. So CPU only does operations inside of itself, but in embedded systems, we usually want to also have some kind of input and output. For example, we want to switch something on or off based on some condition in our program. And to do that, the CPU needs to somehow gain access to physical world. And it is done through something that is called peripherals. So all microcontrollers have peripherals. And I'll just write down some of the most popular peripherals that microcontrollers have. So, for example, GPIO is general purpose.
Input and output.
Input and output, correct. Which is basically the pins of the microcontroller. And you can set them as inputs or outputs. You can set them high or low. You can read their value, whether they are forced low by some external push button or something like that. So general purpose input output. So another thing that the microcontroller can do, we will want to teach the microcontroller to speak to us, to send us some messages. And to do that, we usually use a peripheral called UART, Universal Asynchronous Receive and Transmit Peripheral, which can send text from microcontroller to, for example, CPU. We also have a peripheral called real-time clock, which is used, for example, for timekeeping, to somehow support functions like delay and do something every 5 minutes. So there is this peripheral built in. So in this semester, we will try to use all of these peripherals, learn how they work and what their limitations are, some basic stuff. So to get a mark in this subject, you will need to do two things. First, do labs. To do the labs, you will receive a development kit from school, which has part number STK3700. So where is the picture? Okay, so from school, you will receive this development kit, which is manufactured by Silicon Labs, which is a very decent microcontroller manufacturer. And on this development kit, you will have a microcontroller and some buttons, some LEDs, a light sensor, and something like that. And we will try to program it, make it do something for us, and so on. So to get this development kit, you'll need to sign a document that you have received it and that you will not break it, and you will receive it to work with it at home or in dormitories, because we will not have labs in school because of this COVID situation. So first, I think 4 or 5 weeks, starting next week, these development kits will be at another group of students that also have this subject. And after they do all labs, they will give these development kits back to me, and I will hand them out to you. So your lab starts after something like 6 weeks, and you will have approximately 5 weeks to do the labs. So we have, I think, 8 or 16 labs together, but they are not very complicated. They're pretty easy, and you can just sit down, do them in a few days, and hand them in. So neither of these labs takes a whole week to do. So, you will have plenty of time to do the labs. So first thing is this: you will receive development kit, you will do labs. And the second thing that you will need to do is do tests on Artus. So in best case scenario, I cannot promise you that I'll do it every time, but after most lectures, you'll have a test in Artus about the topic that we studied, and you just need to fill the test. The test will automatically be graded. You have unlimited amount of tries to do the test. So because the test's goal is not to punish you for wrong answers, the test's goal is for you to learn from your mistakes. So you do the test, you see which answers were wrong, you go on the internet and read something more about them, and then you try to do the test again until you score as many points as you want. So maximum is 10. So you can do it, for example, 5 times, and with 5th time, you will probably get all the answers right. So these two things. And at the end of semester, I will check out the labs, the tests, and I'll just put you the mark. And I think you will not have any kind of exam. Just do the labs and the tests, and you will be fine. And we will also have these lectures. In the lectures, I'll tell you some theory about the microcontrollers, or I'll share my experience while working with microcontrollers. I have worked in 5 different companies for the last 10 years with microcontrollers. We have had some problems, some solutions, some interesting cases where we approach the limits of the microcontrollers and their peripherals. So I have some things to share with you. You'll gain some knowledge and some experience from that. So I suggest that you connect to the lessons, to the lectures, and tune in and listen to them. Maybe you'll learn something. Okay, so that's that. And now we will just start talking about the microcontrollers. So as I saw in the chat, some of you have had some experience with various manufacturers of microcontrollers. We have Atmel, Arduino microcontrollers. We also have PIC and MSP 430 from Texas Instruments. And the Silicon Labs builds microcontrollers. So there are very many manufacturers, and there are very many kinds of microcontrollers. Some are extremely small, very few features, but also extremely low cost. And then there are very big microcontrollers with lots of features, huge memory, lots of peripherals. So each microcontroller has its own right place in a project. In these labs, we will be programming on these Silicon Labs microcontrollers EFM32, which basically says it is a 32-bit microcontroller. 1 second. I'm sorry, 1 second. I have a carrier. I need to receive a package. And so the reason that we're using this Silicon Labs development kit instead of STM32 from ST Microelectronics or Arduino or something like that, There are several reasons. First of which is that this development kit contains current measurement software and current measurement hardware. So when we write a program, we can measure how many milliamps or microamps this microcontroller is consuming, because Silicon Labs is focusing mainly on extremely low power applications. So these are battery operated applications. So for example, they say that with this small coin battery, you can do some calculations with the microcontroller and also have this LCD turned on, and it will only consume a few microamps and it will work for several years. So they are focusing on low power consumption mobile microcontrollers. So they have development kit which has built-in current measurement. So it is called Silicon Labs Energy Profiler. Let's see, maybe it has some pictures. So yeah, and they have this view in Simplicity Studio where you can measure with this development kit how much electricity the circuit consumes. Okay, so that's the main reason. I don't know any other development kit which has these features, but if you're developing a device that runs on battery, you need to measure the current consumption. You need to make sure that the microcontroller is really sleeping in low energy mode and it's not draining the battery quickly. So that's why we have these development kits. And also Silicon Labs has great example projects and great libraries. So basically, if you want to build something, you buy their chip, you look at their website, and you can find a very beautiful, nice example for almost any functionality that this chip has. And just copy the code from the example project to your project, just do some minor changes, and it works. Unlike many other microcontrollers, which are maybe €1 cheaper or 50 cents cheaper, but have no examples, and you buy the chip, you put it in the schematic, and when you have to program it, you don't know how to do it because there are no examples. So yes, Silicon Labs chips are not the cheapest, but they have great examples and also they have support. So if you're programming something doesn't work, or you think that there is a bug in the microcontroller code, you can contact support, and within a few days, they will answer you, look into your problem, and give you a solution. So, you know, this, you have to pay a little money for that. Okay, so more information about these microcontrollers you will get as you do the labs. So we will not have labs in Zoom because you don't have the development kits yet. So what I will do is I will record the labs, I will prepare lab descriptions, I will put them in Ortus, but you only do them after 6 weeks when you get the development kits. So according to our schedule, I'll just check out when we have the lessons, and I'll tell you which ones we will have and which ones you will have like on your own. So let's see, our subject is this, and schedule is here, Monday, Tuesday, Wednesday. So we have lecture every week, and we have lab, I guess, every other week. So this second lesson we do not have from 16:30 to 18:05. We don't have it. And after 6 weeks, you will do the labs. And when you do the labs, I will have Zoom turned on during this period of time. So if you need some assistance, you connect to Zoom and ask me questions. But generally, you can also do the labs in weekends or whenever you have free time. So this time you can kind of use for consultations. I will be available, but you can also contact me on email and so on. So we will only in person through Zoom have this first lesson.
Sir, just a small question. Like, so you're saying that we are not going to have the second lesson until the sixth week?
Yes, and starting, I think sixth or seventh, I will I
Okay.
will look at how quickly the other group returns me the development kits, but hopefully in sixth week. And
Okay.
in sixth week, I will be available at this time to ask questions, but I will not make a lesson because I will have pre-prepared the descriptions of the labs, just like in the previous semester. I think it was the same. I put the lab video in YouTube, and you could do it on any free time, but I was available in this time for questions.
Okay, sir. Got it.
Mhm. Because some people, for example, just do all the labs in the first day, hand them in, and they don't want to, they want to just forget about this subject. So no need to make a fake lesson there. Okay, so that's about the labs and development kits. So, and now we need to look at the first peripheral that the microcontroller has and that everybody uses, and it is general purpose input output and its modes and how it works and things that you really need to take into consideration while designing. And many people make very, very silly, simple mistakes because they just tend to forget about the internal working of general purpose input and output. So, uh, general purpose input output peripheral um, basically does, just a couple of things. GPIO. So first of all, generally speaking, you select whether the microcontroller pin input or output. So you can have it as input where you can read whether it's low or high based on the signal forced onto the pin, or you can connect some LED and set the output high or low to turn on or off the LED. So you can select whether it's input or output. It's called direction. And the second thing that you can do is if output, oops, output, select low or high. Okay, so very simple. Now let's check out how the general purpose input output is organized in these microcontrollers. And you'll see that there are actually very many features. And we will look at the general purpose input and output through the prism of this microcontroller that we will have in our labs. So it says that this development kit has this microcontroller, which you can buy on the internet if you want, so it's not a big problem. And it costs, for example, 1,000 pieces, €6. So this is a pretty high-end microcontroller. And we have it in lab because we want to have, to learn as many features as possible. But these Silicon Labs also has cheaper versions with less features. So not all microcontrollers are this expensive. But what we need to do with this microcontroller, we need to use two documents that describe the internal parts of this microcontroller. The first one is datasheet. All microcontrollers have a datasheet. And the second, under documentation, is a reference manual of this microcontroller. So in datasheet, we have information about electrical characteristics of this microcontroller. For example, how much electricity does it consume while sleeping? What is its maximum speed? For example, these are, I think, 48 megahertz processors. We know what kinds of internal peripherals they have. And in the reference manual, it describes how each of the peripherals works. For example, let's see, a peripheral called low energy UART. So as you can see, it has 842 pages, so a lot of peripherals. Here it is, for example, UART, Universal Asynchronous Receiver Transmitter, and it describes how this peripheral works, how many features it has, for example, that it can send from 4 to 16 data bits. Some other microcontrollers, for example, you can choose only 7, 8, or 9 data bits, and so on. So this describes the features. And we will just go through the main, most common peripherals, and we will study their features. It's not really that complicated. And just do it in small baby steps. Okay, and datasheet is electrical parameters. And now I will open reference manual in a PDF viewer, because this reference manual also has, um, bookmarks. So for example, I want to read about general purpose register, general purpose input and output, and I can just click on it and it goes to the corresponding page. And so the general purpose input output in this microcontroller has very many features. I would say too many features, out of which we will only use some like 3 features, but it's just that the microcontrollers are just being upgraded and upgraded all the time. They get more and more complicated, and to the point where it's just so complicated that it's hard to follow. Um, so this microcontroller, for example, when you reset it, all pins are inputs, so that if you have connected some switch, the microcontroller doesn't switch the switch on or off. It's just as input, so it's off. Um, and if you want to do some switching, you first need to set it to output. And in this microcontroller world, output is called push-pull, because you either push the output high or pull it low. And you can also have open drain output where only bottom transistor works, or you can also have pull-up resistor, pull-down resistor. Previously, microcontrollers had only pull-up resistors, but now, since their technology advances, we also have pull-down resistors in many microcontrollers. Silicon Labs chips are really good because you can also control the drive strength of the output, how many milliamps you want to push through the pin. And it has 4 levels: high, standard, low, and lowest. And in datasheet, we can go to page which describes electrical characteristics, general purpose input output. And in datasheet, it also tells you what it means: lowest, low, standard, and high output current based on supply voltage. So these microcontrollers have a current limiter on each pin, So you can actually limit the current, which is good. You can connect, for example, an LED directly to the pin, and you can control how much current will flow through it, and the pin will lower its current automatically to match what you have set, so that you don't have to put a resistor in series with LED. You can save on the component count, because you can connect a load directly to the pin and just limit the current. Just be careful. These graphs have different supply voltages. And the most common voltage that usually is fed into microcontroller is 3.3 volts. Let's see. So for 3 volt supply voltage, we have, if we set the current, the pin low, basically you can see at 3 volts, the lowest, on the lowest setting, the current is just 0.4 milliamps. So it's a small current. You can connect LED and it will shine in a not very bright manner. In low setting, it's 8 milliamps. In standard, it is 35 milliamps. So you can drive, for example, optocoupler directly with the microcontroller pin. And in high, the current limiter is off. So as you can see, the current can be as high as 50 milliamps or even more. Okay. And for sinking capacity, if you said, for draining capacity, if you set high level, then the current is 0.4, 5 milliamps, 40, and maybe 100 milliamps at higher loads. And it's a good cool feature, and you will try to use it in the labs and you will see its benefit. So that's about current limiting. You have also special functions for the pins. For example, they can be inputs to analog to digital converters and so on. And now let's check out the internal part of the GPIO. Here is more or less full schematic about the general purpose pin functionality, but I will redraw it slowly on this whiteboard, and we will see the implications of the general purpose pins. So the general purpose input output pin, let's draw it like this. So the left part is inside the microcontroller MCU, and the right side is outside world. And so outside of microcontroller, you just see a pin of a microcontroller. And you can solder a wire to it and connect it to LED, or you can connect it to a switch if you want to use it as input. But here's what you need to know about the internal part. So first of all, each pin has electrostatic discharge protection diodes. One is like this, and one is like this. So I'll write it here, ESD, with small letters. And this top part is connected to power supply. And the bottom part, bottom end, is connected to ground. So these electrostatic discharge diodes serve for several purposes. First is inside of the manufacturing plant, when people take the PCB and put it in the enclosure, touching the schematic, a person can accidentally hit the chip with electrostatic uh, energy. So, for example, you have a synthetic or wool sweater and you move around, and you have also a chair with some synthetic material on it, and you charge yourself with electrostatic charge. And when you touch the board, you can accidentally hit the microcontroller with electrostatic electricity. Okay, so if you touch the pin with your finger and it is hit with electrostatic discharge, what can happen is this spark can go into microcontroller and damage it and destroy it. And so since microcontrollers get smaller and smaller, their cores get smaller and smaller, and also, for example, that the newest Apple M1 chip is just 5 nanometer technology with very, very small transistors. Even a small electrostatic discharge would just evaporate the transistors and the chip would be permanently damaged. So for this reason, each pin has these electrostatic discharge protection diodes, and so when you touch the board, if you are charged, the electricity goes, instead of going through the CPU, it goes through the ESD diodes, either to ground or to power supply voltage, which has a large capacitor connected to it. And this charge just goes into the capacitor or somewhere else and doesn't go through the internal parts of the microcontroller, right? um, so after these diodes, we have the MOSFET switches, which push or pull the pin low or high. So in the up part, we have a P channel MOSFET, and in the bottom part, we have N-channel MOSFET to ground. Da, da, da. So this is P channel and this is N channel MOSFET. And so inside of your code, you can tell whether the pin should be high or low. And if it needs to be high, then P channel MOSFET opens and connects the pin to power supply. And when you want it to be low, P MOSFET is closed and MOSFET is open, and the pin is connected to the ground. It's low level. And as I mentioned, these EFM32 microcontrollers also have current limiter, but many microcontrollers don't have that feature. So I will not draw it in this picture. And also, there's a small series resistance also for protection against short circuits and electrostatic discharge. And also, so these MOSFETs are used for um, output, but if you want to use it as an input, then just both of these MOSFETs are shut off. And then for reading the input, there is a Schmit Trigger circuit, uh, which gives signal deeper into microcontroller. So you can read what the level is, and if the level is approximately the middle between power supply and ground, then this Schmit trigger has a small hysteresis and it doesn't just wobble around quickly. And you can check out its value in the datasheet. Let's see, datasheet, and it tells you that, for example, any voltage that is lower than 0.3 times supply voltage will be considered a stable low input level, and any voltage above 0.7 times power supply voltage will be considered as high, and everything in between is a non-stable value. So if you want to use it as input, you have to make sure that the signal that is coming to the microcontroller is within these limits. And you can also check out what is the hysteresis of the signal. It is 0.1 times power supply voltage. Okay. You also have the maximum output fall time. So how quickly the pin goes low or high. It has some limitation. And let's check out to what frequency it corresponds. So 250 nanoseconds is 0.1. So 250 nanoseconds corresponds to 4 megahertz speed. So if you set the pin high, low at faster frequency than 4 megahertz, well, it's not going to be a beautiful square wave. It will be more like a, just wobbling around the middle. So you just have to, take it into the account if you need fast switching outputs. Also, the microcontrollers, when you use them as inputs, you can also turn on or off their pull up and pull down resistors. So there is a resistor and a small MOSFET, which enables or disables the pull up resistor, and also the same for bottom part. And they can be switched on or off independently. So for example, if you connect a button to the pin, a switch to ground, and you enable this pull-up resistor, then microcontroller pulls this pin high all the time, and when you press the button, it pulls the pin low. There is some current that flows from supply through the pull-up resistor to the ground, but the current is very small. The input buffer sees that the pin is low, so it knows it's in a stable low level, and when you release the button, then this pin is released and this pull-up resistor pulls the value of the pin back up through this resistor. And in the datasheet, you can check out that the value is 40 kilo ohms. And actually, if you're like really cheap, you can also use this to shine a small LED. You can, for example, connect a diode, a small LED to the ground. And instead of putting it as output, high or low, you can just turn on or off the pull-up resistor. And this way, you don't need an external resistor for LED. The only thing that you need to do is you need to calculate the current for, what current will flow through this circuit. So if the pull-up resistor is 40 kilo ohms and it's short to the ground, then 3.3 volts divided by 40,000 is 82 microamps, which is a very small current, right? And if you are working with LEDs, the voltage on, for example, red LED is 1.8 volts. So you would also need to subtract that 3.3 minus 1.8 is this divided by 40,000 is only 37 microamps. So very small current. However, modern LEDs are so bright that even a small current actually displays some light. So you can do it if you're really, really cheap and you don't want to put an external resistor. Okay, so we have input, output, pin, which can be used for both input and output. Um, and now, another thing that we need to remember is the second meaning of these electrostatic discharge diodes. So they are simple diodes. Normally, they don't conduct any electricity, but let's say that we have supply voltage, for example, 3.3 volts. What happens if we connect a pin accidentally, for example, to 5 volts? So this electrostatic discharge diode is meant also to protect against overvoltage and undervoltage of pin. So when we connect 5 volts, um, electricity, current goes into the pin through the ESD diode to the supply of 3.3 volt. So this diode has a voltage drop of approximately 0.7 volts, just simple silicon diodes. And the supply voltage increases to 3.5 minus 0.7 volts. There's also this 200 ohm resistance in the path. So oftentimes, if you accidentally connect a pin to a higher voltage, the microcontroller doesn't explode immediately because there is this protection. So the current initially flows through the ESD diode into the power supply. And for example, if you didn't connect it directly to 5 volts, but you connect it to some weak signal, which is 5-volt biased, maybe your microcontroller doesn't even burn immediately. Um, it's just that after a couple of seconds, if the current is big, then this diode heats up, burns, and then the current goes into the processor and burns the internals. So these ESD diodes sometimes protect the microcontroller against users' mistakes, even if you connect a higher voltage. If it's weak, if it has big internal resistance, then nothing bad fortunately happens, at least not initially. If you keep it that way for longer times, then of course it's damaged. And the second option, if you connect the pin to, for example, minus 5 volts, so then the second ESD works. So here is 0 volts. The current flows from higher volts to lower volts. So it flows through this ESD diode down to minus 5 volts. And again, if you have some weak signal of minus 5 volts, which has internal resistance, maybe again, the microcontroller will not burn immediately. It will just heat up this diode and this resistance, and maybe nothing bad will happen. So these diodes are actually really good. However, sometimes they cause problems with leakage currents. And now I will demonstrate you a case where these ESD diodes at the same time help and don't help and bother. So let's say you have a very typical system where you have a battery, which is a rechargeable lithium ion battery. Lithium ion rechargeable battery. What is um, the what is the voltage of a rechargeable lithium ion battery? Can you tell me?
3.7.
Hmm?
3.7.
Yes, 3.7 is the nominal voltage. But actually, when you charge it to full, it's actually more volts. So actually, do you know how many volts?
I think it's around 4.2 or something.
Yes, 4.2 volts when it's absolutely totally full. And when it's empty,
2 point, I don't know. Yes, it's around that range. 1.8 or 1.7.
actually, if you short circuit it to ground, it will charge it will charge down to 0 volts. But if you charge it very low, discharge it very low, it's
Damage the battery.
yes, it will damage the battery. The internal chemicals react. Some hard salts form, and it just loses its capacity. It's useless. You can throw it in the trash. So all batteries have, at least all good batteries have, internal protection circuit, which turns the battery completely off, disconnects it from the world if you discharge it to 3 volts. It's for its own protection. Your software should switch itself off at something like 3.5, 3.4 volts. That's already too low. But if your microcontroller, for example, hangs and doesn't do it, then batteries have protection circuit inside, which automatically just switches them off. There's a small board. You can actually check it out on the internet. Leon Protection. Um, so in many batteries, there's actually this small board next to the battery. Let's see, TME. Mm-hmm. Here. So these flat batteries, where are they? I'll show you an example. I don't know if these cylindrical ones have that protection actually. I haven't really opened them. But for example, these behind this black plastic where these wires come out, there is hidden that small board which has protection. I wonder. There are some good pictures someplace. Just can't find them. Okay. So I don't know if these round batteries have that protection.
No, sir. The 18650 do not have those protections. The cylindrical 18650 batteries, they don't have that protection. We should build that for that. Or we should use an external circuit.
Yes, you should put a protection circuit on the PCB,
Yes.
but the problem is that just in another project, we had problems certifying these batteries because during the tests, they short circuit the battery and the battery may not explode or burst in flames. It's forbidden. So
Yes.
I don't recommend using these batteries because you
Batteries.
can have serious problems with certification.
And they have problems while charging also, like the balance charging, when you have more than 2 or 3 batteries.
Yes, but it's true for any battery, cylindrical or flat. These cylindrical batteries, they have good properties also. The cylindrical batteries are built naturally by taking, the lithium and these separators and just rolling them. So it has a very stable form, cylindrical metal shield, so they are actually more robust. These flat batteries are actually built from the round batteries, which are just compressed flat. And during this compression, they can get damaged and actually are not as safe. So, one battery has one advantage and the other battery unfortunately has another advantage which the first one doesn't have. So that is like a little bit of engineering choice that you have to make, a decision. mm. Hmm? Okay. um, but as we were talking, this battery can have 4.2 volts, 3.7 down to 3 volts. If we check out our microcontroller under operating general operating conditions, it basically tells here that this microcontroller works from 1.98 volts to 3.8 volts. So we cannot connect it directly to the lithium ion rechargeable battery. So we need to put either a switch mode power supply, or usually it's much cheaper to put a low dropout regulator, LDO. And it accepts whatever voltage comes in and, for example, puts out 3.3 volts, right? And we can connect them directly to the microcontroller. MCU. Okay, and it just works. The microcontroller also has ground and it has a capacitor here. Okay, so this microcontroller gets 3.3 volts from battery. Now, in many applications, we want to measure the voltage of the battery to understand how full it is. For example, if we measure 4.2 volts, we know that the battery is absolutely full. If we measure 3.7, we know that, okay, it's good, it's something like 50%. And if it's under 3.5 volts, we know that it's empty. So, we should just switch off the microcontroller should switch itself off, and we need to wait until the battery is recharged. But we cannot connect the battery directly to microcontroller because the voltage of battery is bigger than microcontroller's supply battery, and it's forbidden. It will burn the microcontroller. It will damage it. Batteries have very strong output, so there's no way we can just connect them directly to the microcontroller. So what can we do? Do you have any ideas? How to measure battery voltage if battery voltage is higher than microcontroller's voltage? Okay, so the simple thing.
We can discharge the battery across a resistor and measure the resistance. No, we can discharge across a resistor and then measure the voltage. Current through the resistor actually. And then is it possible to use it to find the battery voltage?
Okay. Yes, you would just connect two resistors. Well,
voltage divider circuit.
Yes, exactly. You would use a voltage divider circuit. And you can actually connect two equal size resistors for example, 100 kilo ohms and 100 kilo ohms, they are big, so they don't consume a lot of electricity, they don't load the battery too much, and the midpoint is just 1/2 of battery voltage. So instead of 4.2, it will be 2.1 down to 1.5 volts. And you can just connect it to microcontroller and measure it, right? But is there a disadvantage of this circuit?
Theoretically, it seems okay, but practically there will be some energy lost in this process, right?
Exactly. So even though it's 100 kilo ohm resistors, they actually consume some electricity, and they will discharge the battery. And unfortunately, even though you might take a calculator and you can, for example, calculate what the discharge will be. So I don't know. So it's 4.2 volts divided by 200 kilo ohms times 1 million, you get 21 microamp. And you might think, oh, 21 microamp is such a small current, right? Let's say you know, um, a typical battery size that is often used is something like, for example, 30, 40, 50 battery. I think this size, yeah, here it is. So for example, this battery, and also you can see here that there's this protection circuit.
Okay.
So this is like a regular size battery, which is 5 centimeters thick and 30 by 40 millimeters um, wide and high. So these batteries are oftentimes used in many devices. So I'm just giving it as an example. And their capacity is 600 milliamp hours. So if we have 600 milliamp hours divided by 0.021 milliamps, we get that they work this many hours. So divided by 24 hours is this many days, and we divide it by 365. And theoretically, the device will work for 3 years until it drains the battery empty. But unfortunately, in reality, uh, you maybe you have more than one such resistor divider, and also the battery has a self-discharge, which is approximately 2% per month. So actually, and maybe, for example, this LDO also has some quiescent current. And basically, if we add all of these small currents up, actually the battery might discharge itself through these resistor dividers within something like a year. And that is a serious problem, because when you buy batteries, they cannot be shipped full. The law says that if you want to ship the battery, it needs to be under 30% full. So it's almost empty when you receive it. And then these small parasitic currents through these resistor dividers, they also empty it. And for example, you produce 1,000 devices, and they sit in stock in your, in your stock for half a year until you sell them. And during this half a year or 1 year, it's possible that these resistor dividers actually empty the battery to a point where it is damaged. So we don't want to use these kinds of resistor dividers as much as possible. We want to put some kind of switch to turn it off so it doesn't consume any electricity when we don't want it to,
So
right?
then, yeah, if we add a transistor onto the connected to the MCU, which will be in the off position, and whenever we want to read the battery voltage, we can switch on the transistor so that the line is connected and we can measure the battery.
Exactly. You are absolutely correct. We just need to put a transistor in this circuit. The question is, where should I put the transistor?
On the top of the first 100K resistor. Oh yeah, right over there. I think that would be the perfect. It would cut off the battery and the connection to the resistor that way.
Okay, that is a very good answer. So for those of you who don't believe that this is the best position, maybe you, for example, are lazy and you think, now I'll draw the wrong way. Maybe many junior electronics engineers just connect the transistor in the bottom part because it's easier. You can get the N. This is N-channel MOSFET, right? And N-channel MOSFETs are cheaper, they're widely available, and you can just set high to turn it on and set low to turn it off, right? So this N-channel resistor, many people do this, but it is a mistake because when the transistor is on, here is 4.2 volts, the current flows through the resistors and the transistor. Transistor is like a switch. It has 0 ohm resistance, practically 0 ohms. And, there's no voltage. So 0 volt voltage drop. So, you can just imagine that it's just connection without resistance. And the mid part is 2.1 to 1.5 volts, which is correct. Everything works correctly so far. But if we switch the transistor off, it acts as an open circuit. So basically, we just cut off this part because, transistor is off. It means that it's open circuit. And what happens is, so here is 4.2 volts. And if the current is 0, then the opposite end of the resistor also becomes 4.2 volts. Do you agree with that? So voltage on resistor is equal to current times resistance. Resistance is 100K, but the current is 0. So voltage on the resistor is 0 volts. So it means that both ends of a resistor have the same voltage. There's no voltage drop. So this point through this resistor actually becomes 4.2 volts. And as a result, through this resistor, we are touching the microcontroller with 4.2 volt voltage, and the current flows through the resistor, through the ESD protection diode, into the microcontroller's power supply. And actually, this leakage current, because here is 3.3 volts, then we have a diode, and here is 4.2 volts. So, okay, because of the voltage drop on the resistor, there will be less than 4.2 volts, but but higher than 3.3. So you can see that here's 4.2 volts, and they flow through the top resistor, through electrostatic discharge diode, into the power supply, which is 3.3 volts. And actually, this adds up so that this LDO actually consumes double the current. Some current is the input current, and then the secondary current also going through. And this leakage is actually something like 200 microamps. And even though you think that you have disconnected this resistor divider, it actually starts to consume more. And I have seen this mistake many, many times. So you are absolutely correct. You need to cut off the voltage at the high end, not the bottom end, because from the top end, it will just leak through the microcontroller's ESD protection diodes into the supply. Some microcontrollers, for this reason, have removed some of these electrostatic discharge diodes, and then they write that this pin is, for example, 5 volt tolerant. It just means that it doesn't have this ESD protection diode. Since there's no diode, you can connect it to up to 5 volts and there will be no leakage current. But the problem is that as soon as somebody accidentally touches the pin with electrostatically charged finger, maybe it's an installation person or in manufacturing plant, accidents happen all the time. So they touch it and the microcontroller is dead. So it's not such a great idea to remove these electrostatic discharge diodes, but they do bother when you connect higher voltage through a resistor and you don't notice it, right? So you're absolutely correct that you need to put the transistor on the top side. So let's try to do that. And let's try to do it correctly, okay? So So instead of connecting it to the bottom part, let's connect a P-channel MOSFET on the top part. You just have to remember always and always, N-channel MOSFETs connect to the bottom part and only P-channel MOSFETs can connect to the top part, and only in some microchips, only in some chips you can connect N-channel MOSFET on the top part because the chip has charge pump inside. In all other cases, you can do that. So in the top part, we will connect a P-channel MOSFET, okay? I just see so many times when people think, oh, I'll just connect N-channel MOSFET on the top part. No, you won't. It's impossible. It will not work. The device will work in the wrong manner. And even old senior engineers sometimes make this mistake. Just recently had to correct one such mistake. So P-channel MOSFET, P-channel and substrate. So arrow is this. I'll also draw this internal built-in reverse diode, which is automatically inside all of the MOSFETs, so that you see that the current doesn't flow from the secondary side to the primary side. Now, the question is, so just to make sure that I don't come up with some wrong stuff, you're telling that this MOSFET should be connected here. Where do I connect the MOSFET's gate?
To another input to another GPIO of the MCU, I guess.
Okay, let's check it out. You said it, I didn't. So I connect it to another GPIO. So when I set the GPIO high, the MOSFET will be closed.
Okay.
And when I set it low, it will open, right?
Yes, it should. Yeah.
But here is the problem. The voltage on the source pin of this MOSFET, 4.2 volts. I actually need this pin to be 4.2 volts to fully shut it, but the microcontroller only has 3.3 volts. So the voltage between source and gate is 4.2 minus 3.3 is 0.9 volts, okay? I cannot get it to 0 because then I would need to force microcontroller output voltage to 4.2, and it's not possible because it's connected to 3.3 volts. And the problem is that if the voltage between source and gate of the MOSFET is not 0, but something bigger, this MOSFET starts to open. And yes, there is a theoretical threshold voltage for example, 1 volt or 1.5 volt, but 0.9 volts actually starts to open this MOSFET a little bit, and even in off position, because this voltage between source and gate is not 0, but something bigger, there will be some small leakage current flowing through even at the off position. And we can actually check out how big it will be. Let's check out some P-channel MOSFET. I don't know, just Google it. Maybe there will be some part number N703, maybe, I don't know. Okay, here's some P-channel MOSFET. And we can check out, there is this thing called threshold voltage. Gate source threshold voltage. It is the voltage at which the transistor starts to conduct some kind of voltage. And in this case, at -2 volts, it conducts -250 microamps. Minus because the direction is usually from drain to source in N channel, and in P channel, everything is opposite. You connect it in an opposite manner. So the current is also negative. It's just technicality. But basically, at -2 volts, it's -250 microamps. At 0.9 volts, -0.9 volts, it will be something like maybe a quarter of it. So it will still be something like 50, 70 microamps, which is even worse than if we didn't have the transistor at all. Okay, this resistor divider will, of course, still limit the current, but unfortunately, this transistor is as good as open at that point. So unfortunately, you cannot drive a MOSFET with a voltage that is smaller than MOSFET's input power voltage. Okay, so unfortunately, this is not going to work, but it is almost good. We can do a small
Uh,
modification here. You
so,
can, hmm?
sir, is it possible that we connect a set of capacitor to the gate of the MOSFET so that the overall voltage might increase then?
I don't think so. I don't think it's going to work. But I'll show you another modification that we can use.
Okay, sir.
So instead of connecting it to microcontroller, we will connect the gate of this MOSFET to another MOSFET N-channel MOSFET. And connect the N-channel MOSFET PN like this to the microcontroller. So the protection diode is like this. Okay, so, and also we would add a pull-up resistor between here and here. So for example, again, the same 100K. Let's just use the same resistor. I have this style that I don't use different values of the resistors in every new place. I just try to use the same value everywhere where it's possible. So what happens here is, if this microcontroller has 0 at the output, then this MOSFET is off and doesn't conduct electricity, so it's open circuit. It's like open circuit here. And then this gate through this resistor is connected to source. It discharges and it closes completely, and no current flows through this MOSFET, and this resistor divider is off. However, if I set this output from 0 to 1, then this MOSFET opens. 1 is 3.3 volts. Then this N-channel MOSFET opens. It pulls the gate to ground, and this MOSFET opens fully, and the current flows, and we can measure the current. And when I'm finished measuring, I just set this gate off to 0, and this pull-up resistor pulls the MOSFET, P-channel MOSFET, to 4.2 volts and closes it, and it doesn't conduct electricity. So this is actually the correct schematic to measure voltages that are higher than microcontroller's voltage. And for final finishing touch, you would also connect this N-channel MOSFET's output with a pull-down resistor, external pull-down resistor to ground, so that when microcontroller is in reset state, this MOSFET, N-channel MOSFET, is switched off, pulled off with this bottom 100K, for example, resistor. Okay, so this is actually the correct way to do it. P-channel MOSFET is in the top, and it's opened or closed with an N-channel MOSFET, which is at the bottom relative to ground. And each of these MOSFETs has a resistor between gate and source that keeps them off when the microcontroller is in reset state or is hanged or something like that. And then this P-channel MOSFET turns on or off this resistor divider. So this is the way to do it correctly. And, you know, I just have to tell you this because oftentimes people forget about it. And then they have all of these leakage currents from higher voltage through some big resistor divider into the microcontroller, through the safety diodes, and into the power supply. And then basically, well, when 7 years ago I started to work in a smart home company, the previous engineers had, you know, out of experience, they were really young guys, just as young as I was. They made it in the wrong way, and, you know, we manufactured 5,000 devices, and then when we shipped them to the clients, some like 6-8 months later, clients complained that the batteries were totally empty, and they bought the device, they wanted to use it right away, but they had to charge it for some like 7 hours, you know, because the batteries were completely empty, like 0% empty. And from such a low state, it takes more time to charge the battery to 100%. And they were very, you know, disappointed. Also, we received complaints that the batteries need to be recharged more frequently than we expected. We promised 3 years of battery life, but this leakage actually made the battery to run empty after just 1 year, and we couldn't understand why it is that case. And it turned out that the engineers, previous engineers, just had put the N-channel MOSFET at the bottom of this resistor divider. So there was constantly all the time the leakage from the battery through top resistor into the microcontroller, through the ESD protection diodes into the power supply. So it was just constantly discharging the battery to the point where it was almost damaged. Fortunately, our batteries all have this protection board, so the battery just discharged to 3.0 volts, and then the protection circuit just disconnected it entirely, so it didn't keep damaging itself, but still, it was a disappointment. And every place where I start to work after that, in several other companies, I saw totally the same mistake, you know, so probably it's worth telling you this also in these lectures. And I
Sir,
will
uh, just one question. So, do you think the protection circuit in the battery would it use any current to make sure that it keeps the battery safe? Like,
yes, so the protection circuit consumes electricity, but it is designed in such a way that when it's on, it consumes something like 2 microamps, and when it's off, then I'm not sure, but I think it doesn't consume almost any electricity. But you can actually check it out on the internet. I don't remember the part number, but I can check it out. Um, da, da, da. I actually have worked with these protection chips but they worked a little bit strange. So, 1 second. And bill of materials. Project PCB. Let's open this one. And there will be a circuit. Okay, so in one project, I had to make a wristwatch schematic with some wireless charging and an e-ink display. And there, to have as little space as possible, we had to use an extremely thin battery that did not come with protection circuit. Maybe I have in 3D. Okay, so here you can see we had to buy only an extremely thin cell of lithium battery with just these electrodes, which if you accidentally short them, there's no protection whatsoever, and basically the battery can just explode in your face. But because we needed it to be really thin, as you can see, the thickness of the entire board and battery was something like maybe 1 millimeter, or not one, sorry, it was something like under 3 millimeters. So we couldn't buy it with this huge board of protection. So we had to put the protection on the PCB. So here is the protection chip. So, just visually, here's also the wireless charging chip. Here is a converter for electronic e-ink display, e-ink, and microcontroller with a button. So in the circuit, I can just check out quickly the part number of battery protection circuit, which is this. You can buy them, but I recommend, if you can, just select a pre-certified battery which has protection inside of it. This was a totally unordinary case. So, quiescent current. Of this protection board. Okay, so here it is, current consumption, operating current 3 up to 6 microamp at normal state, and in standby current, when voltage of the battery goes really down, it switches itself off and it's 0.95 microamps, so really, really small. So it does not drain the battery as much as, for example, if you didn't have it. So it's a relatively small impact, but it's true, it does consume some current. So in low power designs, we want the leakage current to be under 10 microamp all combined together. So microcontroller sleep current is, for example, 2 microamps. Maybe you have LCD which consumes 1 microamp. This protection consumes something like 3 up to 6. The total is 10 or less. If it's over 10 microamps, we would not call it low energy application anymore, because the current is too big and the battery life will never reach over several years. So yeah, you can use such chip for protection. And from ST Microelectronics, what a long name. Under products, they have actually a very interesting device. Power management, battery chargers. So normally you would have a battery which has battery protection circuit inside. I'll just draw it here, protection here. Then you have low dropout regulator, and then you have microcontroller. And also for this battery, you also need a charger. So there's a separate chip, which is somewhere here, which you can connect, for example, to micro USB, which is charger. But for very small applications under 200 milliamps, they actually have a chip. Where is it? STBC02. I think it was something like this. So this is a one chip that contains a charger, low dropout power supply, and also protection. But I think STB01 was the best one. This. So they have this chip, linear battery charger with LDO, and also integrated and battery overcharge protection, over discharge protection, and over current protection. So this one chip contains everything that in other systems you would need 3 different chips to do LDO protection and charging. But it doesn't have very high output current. So charge current up to 200 milliamps, and the LDO was something like 50 milliamps. So yes, you can use it for something like a small Bluetooth device, for another small device. But if you need more current, then it's too weak. It's too weak for you to use. LDO output current. Milliamps. It doesn't even say it. Oh yeah, LDO short circuit current 250 milliamps. So, just for your information. Okay, I guess that's all for today. So, yeah,